Hey everyone, I want to take a minute to talk about dependence and independence. So one of the things that I feel like we're struggling with is really asking the question, are they independent events? All right, so one of the ways that we can tell is that if taking two probabilities and multiplying them together, if that equals the probability of having them together, like A and B, then we have yes, they are independent events. So here's an example. If I take the probability of drawing a red card times the probability of drawing an ace, I'm wondering, do I get the probability of drawing an ace and a red card? So let's take a look at this. I know how many red aces there are in a deck. There are 2 out of 52, so 1 out of 26. Probability of a red card in the deck, well, that's 1/2. Probability of an ace in the deck, that's 4 out of 52. So if I multiply these things together, I get 4 out of 104. And if I do a little reducing, I get 2 out of 52 or 1 out of 26. These things match. Notice, I just know the probability. That's how many cards there are. There's 2 of them out of 52. That's me finding that probability just by taking those numbers into account. Here's the calculation. So yes, those are independent. So let's ask that question again. Are they independent? What if I do the probability of drawing a red card and a diamond? All right, so I want to see if that's the probability of drawing a red card times the probability of drawing a diamond. So if we take a look at this, how many red diamonds are there in the deck? Well, there's 13 of them out of 52 total, so that's 1/4. That's the probability I'm looking for. Well, half of the cards are red, 1/4 of the cards are diamonds. That equals 1/8. Notice these are not independent. Really, it probably makes sense. Being a diamond is dependent on you being a red card. You can't have a red without the diamond. All right, so when we take a look at that, those two things, these are not independent events. One of the things that we looked at then was, how do you find the probability of something occurring given that something else happens? So probability of A given that B occurs. That's kind of what this bar means right in here. And we said that in this case, it's the probability that A and B occur out of the entire probability that this happens. So in the case of our red card and a diamond, the probability of drawing a red diamond. All right, so let's take a look at this. There's 2 different ways to see this. There's the probability of drawing a red card if I know it's a diamond, and there's a probability of drawing a diamond if I know it's a red card. Now, if you think through these things, I should know this one. If I'm drawing a red card, what's the probability that a card is red given that it's a diamond? That should be a 100%. All the diamonds are red. This one, if I know the card's red, half of them should be diamonds. So let's take a look at both of these. Probability, and so in this case, A is red card, B is diamond. Probability that it's a red card times the probability that it's a diamond divided by the probability that it's a red card. Or excuse me, divided by the probability that it's a diamond. All right, so the probability of drawing a red card if I know this thing is a diamond, notice we have some problems here. This probability of A and B is not 1/8. All right, the probability of drawing a red card and a diamond, we said that before. To be a red diamond, I actually know that the correct answer for that is 1/4. All All right, because 1/4 of the cards are red diamonds. So this is another example. If I were using, these are dependent events. So because they're dependent events, this does not work. All right, that's why I can't use that. So I have to know how many red diamonds there are, 13 out of 52. Notice I end up with 1, or 100%. Now let's take a look at the probability of drawing a diamond given that it's red. That would end up being, again, a red diamond. I know A and B is 1/4. Red cards is 1/2. If I take a look at this, 1/4 divided by 1/2, 50%. All right, so it makes a difference which one you know. But in all cases, you're saying that I first of all need to know the probability of these two things occurring, you know, given that this other thing happened. So that's some of the issues that I kind of feel like we're having trouble with, is understanding the difference between dependent and independent. All right, so now I want to explain 12.10 again, and I want you to pay really close attention. If you're taking a look at it, in 12.10 it says that 93% of teens are online. Now look at the word choice for this next one. It says that 55% of online teens have posted to a social networking site. And then the last part, it says, of online teens with a profile. So I'm just going to say this over here, of online with profile, 76% have commented on a friend's blog. So I want you to notice that what they're saying here, here's the probability. We're going to say the probability of A is 93%. That is teens are online. So this is A. Here is B. But we are already saying that these teens are online. So that's really the probability of B given that A is already occurred, is 0.55. And this last one, we're telling you that they are online with a profile. So the probability of C, we're going to call this C, given that A and B have already happened, is 0.76. All right, so the general rule of multiplication says that the probability of, well, what does it say? General rule for multiplication, general rule for multiplication. General rule for multiplication. Probability of A and B is equal let's see, it's equal to the probability of A times the probability of B given that A occurs. This is very similar to what we had before. Before we had a special case. Probability in A and B occurring was, we just said, oh, it's probability of A times the probability of B. This member worked for independent events. All right. Here I have things that are not independent. In fact, I know for a fact they're dependent. You can't have posted on a social network unless you are already online. So that's why the special case is what we're using for this one. All right. This is not saying, this does not say 55% of all teens have posted to a social network. This says 55% of online teens have posted to a social network. So in order to put these things together in 12.10, we are basically doing this. We're saying in the first step, 93 times 0.55, and this is the part that they did in the example, and they've got the number here, equals 0.5115. All right, so here is the probability of A and B. So if I want to find the probability of C, given that A and B occurred, I am going to, I'm basically going to say, well, the probability of C given that A and B occurred, I look over here, is 0.76. So if I want to find the probability that all three of these things happened, I'm taking the probability of A, 0.93. Here, let's erase this. I'll do it like this. Alright, so let's take the probability of A, 0.93, times the probability of B, given that A occurred, 0.55, times the probability of C, given that A and B occurred, 0.76. It really is just multiplying those three numbers together. And I will tell you what the result is for that. .39. So 39%. So when we're taking a look at 39% of online teens have posted to social network and commented on their friends' blog. So 39% is what we're taking a look at there, just putting those things together. So again, it really was taking the probability of A and B and C, and it was doing this. Probability of A times the probability of A given that B occurred, times the probability of C given that A and B already happened. So here was the probability of A and B. And here was the probability of C given those two things that happened. We're just multiplying all those things together. So that's what it's kind of doing in terms of that. And a lot of times it's just recognizing how those numbers get placed in there. So hopefully that helps clear up a little bit with the rules about dependence and independence.